Okay, we're going to be looking at problem number 13 on page 460 from chapter 8. This one is giving us a population with a mean of 40, a standard deviation of 5, and no information about the shape of the original population, and the sample size of our, we're going to be taking as samples of size 64. So the first thing it wants to know is the mean of the sampling distribution of the sample mean. Well, as we've mentioned before, the mean is always just going to be of the sampling distribution, since it's an unbiased estimator, will just be equal to the population mean. The second thing it wants to know is the variability of this sampling distribution. In other words, how close we would expect the different values of x bar to be for samples of size 64. To do that, it's going to be 5, which is my standard deviation, divided by the square root of my sample size. So that's 5/8, or about 6.25. Now, for the shape of the sampling distribution, it also is interested in knowing. What we can do on that one is we can say, since I have an m value of 64, which is greater than 30, I can say that n is sufficiently large, and that means that the sampling distribution will be approximately normal. So since n is sufficiently large, and it would be wise, since we're using the central limit theorem, to mention the central limit theorem. The central limit theorem states the sampling distribution of x bar is at least approximately normal. Now, you would be wise not to abbreviate as heavily as I did on an AP exam or one of my tests, but I'm trying to speed things up writing on this tablet. Okay, I'm going to just do a quick sketch of what the sampling distribution of x bar would look like. So this is the sampling distribution of the sample mean with a sample size of 64. It will be centered at 40. One standard deviation was about 0.6. So that gives you an idea of where 1 and 2 standard deviations from the mean would be in the positive and negative direction. 3 standard deviations, of course, will be out here. It's kind of past the range that I've drawn for my graph. So what you're going to find out is that it's going to be clustered around 40 with your inflection points just past 40.5 and just before 39.5, and almost all your data within this middle distribution here. So you're going to have something like this. For your shape and sampling distribution. Now, it's very useful to do this because it wants to know now the probability that I'm within 0.5. So that means the probability that I'm within 40.5 and 39.5. So I'm talking about the probability of being in this pink region here. Now, since that is within, both of those values are within 1 standard deviation of your mean, just eyeballing it, if I know 68% is between here and here, between 1 standard deviation of the mean, I know whatever value I'm looking for is less than 68%. To get the actual value, we're going to need to use a calculator though. So we're starting by, we're going to use the correct notation here. To say I'm looking for a value between 39.5 and 40.5. And both of those are going to be needed to convert it to z-scores. So to convert those to z-scores, I'm going to need to do 39 minus 40 divided by my standard deviation of the sampling distribution, which was not just 5, but 5 divided by the square root of 64. And since this was an exact decimal, it would have been okay to use that. I would recommend, if you get a rounded decimal, to go ahead write it in the exact form like I just did, but in this case, since it's the exact decimal, it doesn't really make a difference if you type in the 0.625 in your calculator or if you type it in as 5 divided by root 64. If you're putting that in your calculator, you might be wise to know that that might need a parenthesis. If you've got one of the newer calculators, it's pretty easy to figure out where the numerator and denominator are, but if you're using one of the older models, that denominator needs to be in parentheses to make sure you're dividing not just by the 5, but by 5 divided by root 64. Now, once you get that, we're going to go ahead and put those in our calculator and get z-scores. So I'm looking for the probability that I have a z-value that is in this range. When you look at the fact our distribution is symmetric, you shouldn't be at all surprised that your z-scores are equidistant from 0, because 0.5 above gives you a z-score of negative 0.8, positive 0.8, 0.5 below is negative 0.8 for my z-scores. Now once I have that to get the actual probabilities, what I'm going to need to do is go to my calculator, and I'm going to be doing normal CDF on my calculator. And with normal CDF on my calculator, your lower bound is going to be negative 0.8, your upper bound is going to be positive 0.8, and then you're always going to, if you're dealing with z-scores, you're always going to leave your mean and standard deviation alone as 0 and 1. For your 0 for your mean, 1 for your standard deviation, so you can put that in the calculator and get your correct final answer. And then for that, what you're going to get your final in your calculator is 0.5762. Now, for part C, it's kind of doing the opposite of what it did in part B. Instead of trying to be in the middle of the distribution, it's going to be on the end of the distribution. So I'm going to erase a few things and show you that. It was asking for differing by more than 0.7, so I have some lines that show about where 0.7 from 40 would be. And you're looking for this pink region on the lower end and this one on the upper end. Now, since approximately normal distributions are symmetric, what I can do is when I'm looking for the probability that x is greater than 40.7, that's also going to be equal to the probability that x is less than 39.3. So pretty much what I can do to save time is when I get the answers to either one of those, I can just multiply it by 2 to get my final answer, because the area in the two tails, since normal distributions are symmetric, is going to be equal anyway. So once again, I'm going to convert that x value to z-score, so I'm going to have 40.7 minus 40 divided by my standard deviation. And once again, since this was an exact decimal, I can just do the 0.625, and that's going to give me the probability of a z-score that is greater than 1.12. And then to get that in the calculator, I'm going to do normal CDF again, and this time my lower bound is I'm starting at 1.22 and I'm going to infinity. So there's several ways to do infinity, but what I like is if I just do 10,000, if I'm in terms of standard deviation, 10,000 standard deviations is more than enough. There's other ways to, you just need some really large number, and once again, 10,000 standard deviations above the mean is ridiculously large and close enough to infinity when you're talking about standard normal distributions and z-values. So that value is going to give you roughly 0.1314. So that's the area up here, and once again, if this area is 0.1314, this area is also, due to the symmetric nature of a distribution, 0.1314. So my total area for my final answer would be these two added together, which gives you a final answer of 0.2628 for your final answer for part C.